Welcome all. In this lecture, we will discuss about the same method, that is the graphical method of solving Cauchy problem for the wave equation. Today we will discuss a new problem. Find the graphs of the solution u x ti for ti is equal to I for I equal to 1 4 comma 4 for the problem utt minus uxx equal to 0 where minus infinity less than x less than infinity and t greater than 0 with the initial conditions u at x0 equal to f of x, which is identically equal to 0, and ut at x0, that is g of x, is equal to 0 if x is less than 0 and it is equal to 1 if x greater than or equal to 0. So we need to find the solution. We have to plot the solution u at x ti for t1 and ux t4. So we need to find the values for x equal to t1 and t equal to t4. We need to plot the graph. Okay. And the initial conditions, the function f of x, the initial data are such that f of x is identically 0 and g of x is have the non-zero value when x is greater than or equal to 0. And we know that by the D'Alembert's formula, the solution uxt is of the form the solution is the solution uxt is equal to, we have 1 by 2 into f of x plus et plus f of x minus et. But here if the function f is 0 and the value of c here from the equation, it is clear that let this be equation number 1. And from the utt minus c square into uxx equal to 1 is the standard form of the homogeneous wave equation. So c is equal to 1 here. So uxt, the sum of the forward and backward wave term, that will be 0. Then the remaining thing in the formula is 1 by 2c, that is c is equal to 1. So 1 by 2 into integral x minus ct, c is equal to 1, x minus t to x plus t g of s ds. Now we know that the function g is defined is a split function with the split is at the point 0. So we can split the integral as, therefore u of xt is equal to 1 by 2 into integral x minus t to 0 g of s ds plus integral 0 to x plus t g of s ds. So we can rewrite this, or we can split the integral as this one. Now consider the function g of x. G of x is a piecewise linear function, isn't it? Piecewise linear function, and g of x, the graph of g of x is maybe like this. When x is less than 0, g of x is equal to 0. So this is for x less than 0, but x equal to 0 value is 1. Let this be the point 1. Then from 1 onwards, then for positive values and for 0, g of x is 1. So this is the graph of g of x. So it is a piecewise linear, piecewise because it is not continuous and differentiable at the point x equal to 0. So this is a piecewise linear function of x, g of s. And now we need to calculate the integral x minus t to 0, x minus t to 0 g of s ds. Actually this is in this one the possible values of g of s are either 0 or 1, and when and we know that this is equal to 1 if g of s when x is greater than or equal to 0, or if we consider the values 0, the upper and lower limits 0 and x minus t, if And we know that if x minus t is less than 0, then what happens? Then the value of g of s, when x minus t is less than 0, that is x is the value of g is equal to 0, then the function integral x minus t to 0 g of s ds will be, we can write it as 0 itself, isn't it? Or we can write this as maximum of what? 0 comma x minus t. Okay, and when x minus t is greater than x minus t is greater than or equal to 0, when x minus t is greater than 0, then g of x integral x minus t to 0 g of s ds, we can write it as x minus t is greater than 0. So minus integral 0 to x minus t g of s ds. In that case, g of s has the value 1. So applying the lower and upper limits, we will get a minus of x minus t. That means minus of maximum of 0 comma x minus t. So in both cases, when x minus t is either less than 0 or greater than or equal to 0, in both the cases we can write integral x minus t to 0 g of s ds in general as minus maximum of 0 comma x minus t. Okay, we can write like this. And similarly, for x plus t, integral 0 to x plus t g of s ds, we can write it as maximum of what? A maximum of 0 comma x plus t. Okay, so maximum of 0 comma x plus t. In the same way, we can write this. So here we have, therefore, u of x comma t is equal to 1 by 2 minus maximum of 0 comma x minus t plus maximum of 0 comma x plus t, or this is equal to minus maximum of 0 comma x minus t by 2 plus maximum of 0 comma x plus t by 2. This is uxt. And since the forward and backward waves are piecewise linear functions of x, the solution uxt is for all t. The solution uxt is also a piecewise smooth function of x. Now we consider the xt plane and try to draw the or plot the solution u of x at t equal to t1 and t4. Okay, for that first we draw the characteristic lines that are emanating from the points where the initial data is not smooth. We know that the two initial data f of x is always smooth because it is equal to 0, and g of x being a piecewise linear function, it has a singularity only at the point x equal to 0, isn't it? So we have to draw, we will draw the in the xt plane. First we will consider the xt plane and we will try to draw the characteristics emanating from x equal to, from the point x equal to 0, as it is the only singularity of the initial data in this problem. Okay. So x equal to 0 is the only point where the initial condition is not smooth, and we try to draw the characteristics that are emanating from the point x equal to 0. And for this problem, we know that the characteristics are given by x plus or minus ct is equal to a constant for in the general case. So here c is equal to 1. So the characteristics are given by the characteristics of this problem are given by x plus or minus ct, that is equal to 1. So x plus or minus ct is equal to a constant. Let it be some k. Okay, so it's equal to a constant, and we know that the initial curve at the initial data for x equal to 0 and for t equal to 0 on the initial data, that is at t equal to 0 when x equals 0, that means the point where the characteristic passes or touches the initial line, that is at the point x equal to 0, we have x plus or minus t is equal to or sorry x plus or minus t, that will be equal to 0. 0 is equal to k, so we have k is equal to 0. Therefore the characteristics are x plus or minus t equal to 0 or x equal to t and x equal to minus t. Okay, so these are the two characteristics uh, of on the xt plane which are emanating from x equal to 0. So if we draw the characteristics or let's try to draw the characteristics on the xt plane. Let this be the xt plane where x is along the horizontal axis and t is along the vertical axis. As in the previous problem, we are taking u along the same t axis, the vertical axis, and now we have to consider the lines t equal to we have to calculate or plot the graphs u at x t1 and u at x t4, and we have t1 equal to ti equal to I, so t1 equal to 1 and t4 equal to 4 itself. So we need to calculate u of x1 and u of x4. We have to plot the graph of these solutions, and for that first of all we consider that x-axis means it is the line t equal to 0. Now we plot the line x t equal to, draw the line t equal to 1. So t equal to 1, let this be the line t equal to 1. Okay, so this is the line t equal to 1. Now for t equal to 4, we need to draw the line also t equal to 4, t4. So for that it passes through the point this one. So for that line, let this is the line t equal to 4. Now we know that the characteristics emanating from the point x equal to 0, and the characteristics are given by x equal to minus t and x equal to t. X equal to t is a line that emanates from 0 and with a positive slope. X equal to minus t is just a mirror image of that one. So let's try to draw that one also. Okay. Sorry. So these are the lines x equal to t and x equal to t and x equal to minus t. Okay. Now we calculate u at these points for t equal to t0, t1 and t4. For that, now at t equal to 0, we have u at x0 equal to minus maximum of 0 comma x by 2 plus maximum of 0 comma x by 2. Since t equal to 0, x minus t will become x and x plus t also will become x. So this is when x is less than 0, then maximum of 0 comma x will be 0. So in both case, we have u at x0 equal to 0. And when x is greater than or equal to 0, u at x is 0. Maximum of 0 comma x will be x. Then the first term will be uh, x minus x by 2, and the second term will be x by 2. Adding this, we will get again as 0. So we can say that at t equal to 0, u at x 0 equal to 0. And hence in the graph, we have the graph of u at x0 can be plotted as this is the point x equal to 0. This is the point x equal to 0, and for x less than 0 and greater than 0, we have um, u at x0 is equal to 0. Okay, so this is the entire the line xt is equal to 0. And since we are taking u along the vertical axis t itself. Okay, so this is the graph of u at x0. Now we need to find the function at the point t equal to at the time t equal to 1. At t equal to t1, that is equal to 1, the forward wave is given by uh, forward wave is given by x plus t is equal to 1. So sorry, x minus t, that is x minus 1, and backward wave is x plus 1. That means the forward wave has that means the forward wave has traveled 1 unit to the right. That means the forward wave has traveled 1 unit to the right, 1 unit to the right, and the backward wave has traveled 1 unit to the left. Now we try to find the support of the two waves and hence the support of the solution. So the support means the support of the forward wave. The support of the forward wave is given by the points were a set of all points for which g of x minus 1 not equal to 0, isn't it? G of x minus 1 not equal to 0, or we have x minus 1, and this that is if and only if this is possible, that is only if we know that by the definition of G, it has a non-zero value for x greater than or equal to 0. So we have, yeah, because this is the function G, and we have G has a non-zero value if x is greater than or equal to 0. So G of x minus 1 not equal to 0 only if x minus 1 is greater than or equal to 0, or x greater than or equal to 1. That means the support of the forward wave is closed interval 1 infinity. Similarly, the support of the backward wave is x plus 1 greater than or equal to 0, that is g of x plus 1 not equal to 0. That means x plus 1 greater than 0 is so x is greater than or equal to minus 1. So x greater than minus 1, so minus 1 to infinity. So the backward wave is support is minus 1 to infinity. So therefore the solution therefore the solution is supported on the union of these two. The support of the solution at a time t equal to t1 equal to 1 is union of minus 1 infinity and 1 infinity, that is closed interval minus 1 to infinity. So this is the support of the solution at the point t equal to t1 minus 1 to infinity. So that means it is clear that in this closed interval u has non-zero value, and outside this interval u will be 0. Okay. So to the left of minus 1, to the left of minus 1, u is equal to 0, and from minus 1 onwards u is positive. U is non-zero. Okay, that we know from this. And the intersection of both the forward wave, the support of the forward and backward wave is given by minus 1 infinity intersection close to 1 infinity, that is the interval minus 1 1. And on this interval, the solution forms a linear function thanks to the backward wave. Now let's try to write the solution at a t equal to 1. That is, at a t equal to 1, the solution u of xt is equal to u of x comma 1, that is equal to minus maximum of 0 comma x minus t. X minus t is x minus 1 by 2 plus maximum of 0 comma x plus 1 by 2. Okay, so this is the solution at x equal to 1. Now, if x belongs to closed interval minus 1 1, that means in the intersection of the support of both forward and backward wave, if x is in this interval, the solution is given by at t equal to 1 is given by x is in minus 1 1 means that means minus 1 less than or equal to x less than or equal to 1. So this implies x minus 1 is less than or equal to 0 considering the right inequality, and considering the left inequality we have x plus 1 also greater than or equal to 0. So if x is in this interval of intersecting interval, x minus 1 will be less than or equal to 0. Now first consider the consider u at x equal to ux1. So the left first term is maximum of 0 comma x minus 1. We know that x minus 1 is less than or equal to 0. So its maximum will be minus 0. So 0 by 2 minus of 0 by 2. Then plus, now x plus 1 is greater than or equal to 0. So maximum will be x plus 1. So this is equal to x plus 1 by 2. So at a time t equal to 1, u at x1, u is given by x plus 1 by 2. So if x is in this closed interval minus 1 to 1, u of x1 is equal to x plus 1 by 2. And if x is outside minus 1, that is if x is less than minus 1, if x is less than minus 1, we know that the support of u is given by closed interval minus 1 to infinity. That means support means the set of all points where u has non-zero values. So outside this interval u must be 0. So when x is less than minus 1, it is outside the interval closed interval minus 1 to infinity. So u must be equal to 0. When x is less than minus 1, u is equal to 0. Now what happens if x is greater than 1? Or now we need to check the case. The only remaining case is x is greater than 1. X is greater than 1. So what happens if x is greater than 1? If x is greater than 1, if x is greater than 1, we have it is clearly x minus 1 will be greater than 0. And since x minus 1 is greater than 0, obviously x plus 1 will also be greater than 0. Then our solution u at x1 is equal to minus of maximum of 0 x minus 1 by 2 plus maximum of 0 comma x plus 1 by 2 becomes minus of x minus 1 greater than 0. So the maximum is x minus 1. So minus of x minus 1 by 2 plus x plus 1 by 2. So minus x by 2 plus x by 2 will get cancelled. 1 by 2 plus 1 by 2, that is equal to 1. So when x is greater than 1, when x is greater than 1, u at x1 is equal to 1. Or we can write u x1 as a split function, that is it is equal to x plus 1 by 2 if x belongs to the closed interval minus 1 to 1, or minus 1 less than or equal to x less than or equal to 1, and it is equal to 1 if x is greater than 1 and 0 otherwise, or if x is less than minus 1 or otherwise, we can write. Now we need to plot. Now it is very easy to plot the graph in the xt plane. So let's do that. uh, so when x is less than minus 1, these are the points minus 1 and minus 1 and sorry, this is plus 1. Okay, this is plus 1, 1 and minus 1. Okay, so and for time t equal to 0, u is all for all values of x, u is equal to 0. So we have the u equal to 0, which is represented with the yellow line. So when t is equal to 0, the graph is u equal to 0. And actually we need to draw the graph of u at time t equal to 1 and time t equal to 4. So first of all, we try to find a graph or plot the graph of u of x1. We have the function. We have formulated the function or defined the function u at x1, and we know that when x is so for convenience, we are using the x-axis along the same horizontal axis. So when t equal to 1, this point is the minus 1, x is equal to minus 1, and this is x equal to plus 1, and this is x equal to 0. Okay, so when x is equal to minus 1 or when x is less than minus 1, we know that u is equal to 0, since the support of u is closed interval minus 1 to infinity. So from this to infinity is the support of u. Okay, so outside this interval means to the left of minus 1, u is equal to 0. So this can be represented. We are using some red line. So this represents u is equal to 0. Let me make some bold line. Okay, so this is u equal to 0, u equal to 0 from minus 1, for x less than minus 1, and when x is greater than 1, when x is greater than 1, the function was u at x1 was equal to 1. So u equal to 1 for x is greater than 1. So u is equal to 1 from where, from 1 to infinity, isn't it? So from here onwards it is u is equal to 1. So this is the line u equal to 1. We know that we also represent u along the vertical axis. So this is the line u equal to 1, and this is the line u equal to 0, and we now we need to mark the graph in the point in the interval minus 1 to 1. So in minus 1 to 1, we have u of u of x1 is equal to u of x1 is equal to minus of x plus 1 by 2. U at x1 is equal to x plus 1 by 2, or this is a line with a positive slope 1 by 2. 1 by 2 plus x 1 by 2 plus x by 2. So when x is equal to 0, it is 1 by 2. U is 1 by 2, and when x is minus 1, it is 0, and when x is plus 1, uh, it is equal to 1. So okay, so these are the points we need to draw the graph like this. Okay. So this is the graph of u. So this is the line u equal to x plus 1 by 2. This represents the line, this one, and u for x greater than 1, it is u equal to 1. The graph is u equal to 1, and for x is less than minus 1, u is equal to 0. So this is the graphical representation of the solution u xt at a time t equal to 1. Similarly, we need to calculate at a time t equal to 4. Now at a time t equal to 4, you can also do this part as the same as below for time t equal to 1. So I'm leaving this part. Support of the, just I'm fastly saying this once. Support of the forward wave, you will get it as x greater than or equal to 4, or x is in closed interval 4 infinity. And for the support of the backward wave is x is greater than or equal to minus 4, and hence the support of u at a time t equal to 4 will be closed interval minus 4 to infinity. Now we try to determine the function u at x comma 4. So when x is in this interval, closed interval minus 4 to 4, we have x plus 4 is greater than 0 and x minus 4 is less than or equal to 0. Then applying the values in these definitions, we can have u at x plus 1, u x comma 1 is equal to x plus 4 by 2, and when x is less than minus 4, obviously u must be equal to 0. When x is greater than 4, we have u is equal to 4, or in total we will have u of x4 as this function. Okay, so this is our u at x comma 4 when it is equal to 0 when x is less than minus 4, and in closed interval minus 4 to 4, value is x plus 4 by 2, and it is equal to 4 for x greater than 4. Now we can plot the graph of the u at time t equal to 4. Uh, So for x is less than, this is the points x equal to minus 4 and x equal to minus 4 and x equal to 4 is here. And so when x is less than minus 4, we have u equal to 0, since the support of u is closed interval minus 4 to infinity for t equal to 4. Okay. So when x is less than minus 4, this will be u is equal to 0. Let's draw this with the white line itself, dark white line. So this is equal to 0 when t is equal to, sorry, when x is less than minus 4. Okay. And when x is um, when x is greater than 4, we obtained u as 4 itself. So from this is the point u equal to 4 4. So from this point onwards, u is the line, or u is equal to 4. Okay, let's draw with the line itself. This is the point. Okay, so this will be the correct point. So from this onwards, this is the graph. Okay, so this is a line um, u equal to 4. Now in closed interval minus 4 to 4, we have u is equal to x plus 4 by 2. When x is 0, it is u equal to 2. So it passes through 2 also. Sorry. So minus 4 to 4, we can draw it as, okay. We can draw like this. Okay. Sorry, this. Okay. So this is the graph of u at x time t equal to t1. This is the line u equal to 4. This is the line where u is equal to x plus 4 by 2, and this is the line u equal to 0. So this about the solution, and this about the plotting of the solutions. There may be some um, mistakes in the drawing due to some difference in the units measurements. Okay, so this will be the um, method of drawing the graphs for solutions at various times given. Okay. So we have drawn the graph of both the solution uxt at t is equal to 1, and also for t equal to um, t equal to 1, and also for t equal to 4. And for t equal to 1, we have obtained u of x1 as it's equal to 0 if x is less than minus 1. It's equal to x plus 1 by 2 when minus 1 less than or equal to x less than or equal to 1. And it is equal to 1 if x is greater than 1. Okay, thus we have already obtained. And for a t equal to 4, we have obtained the ux4 as in the same way. So from these two functions, or two values of u at x comma 4, at x comma t, t equal to t naught, we can generalize, or we can write the solution u explicitly as, we can write u explicitly as u at xt for any time t. We can write it as it is equal to 0 if x is less than minus t, and it is equal to x plus, when t is equal to time equal to 1, it is x plus 1 by 2, and when time is equal to 4, it was x plus 4 by 2. So when for any time t, it was it is equal to x plus t by 2 when minus t less than or x less than or equal to t, and it's equal to t if x is greater than t. So this is the solution in the explicit form. And note that the solution for each fixed x naught belong to R, and for each fixed x naught belong to R, the real numbers, note that the solution u at x naught, the solution u um, x naught t is not bounded, is not bounded because it define it when x is a constant or when x is fixed, it depends upon uxt depends upon the value of t. So when for a fixed x naught, also if x naught is fixed, even though the x naught x is fixed, the solution u x naught t is cannot be, may not be bounded. So in this way we can find the solution, the graph find the solution of the Cauchy problem by a graphical method, so that the things get more clear and easier. So please try to do the exercise problems regarding this. Okay, let's stop here. Thank you. Thank you all.